Yeah, hi, good evening, everyone. So, today we have this session for week 8, basically. So, have you watched the week 8 lecture? The,
Sir, off.
the week 8 lectures?
Sir, week 8 not started.
Not yet.
Doing only. Yeah, no, sir. Doing 7.
Okay, okay. 7 is just a assignments, no? No contents are there. So, have you submitted the assignments of week 7? All assignments?
Yes, sir.
Okay, that's fine. Okay. So this week I have one experiment for UART actually, that UART. So that we will discuss. Otherwise, in week 8, Professor have discussed about some that project structure, designing, how the how the project should design. So we will also discuss regarding that. Okay, so how we can create project, what should be the structure of the project, and what are the other things we need. We can also just enter into when we will discuss about this structures of the project, then we will discuss, okay, what are the proper good structure actually. So we will start from this UART, that experiment today with the board. So if anyone have any question, any query before that, please ask. So I'll show you this UART demo by two methods. First is simple register level programming. Another is that hardware abstract layer that is provided by this STM and that HAL. Okay, so we can directly configure for the pins, and then we can check the code. Okay, so then we will understand that how the project actually created, and how after that how applications actually created. Uh, okay, what are the structure actually we used. So I have connected my board, so that today is actually nothing, no need to visible anything on the board actually. So we will see the output on the screen itself. So I'm not connecting any other camera for the board. Okay, only this same board I'm using as the previous session. That is only simply connected through the computer.
Board is not visible.
Yeah, so board actually nothing, no need to show you through the board actually today. Okay, so the board is connected by the USB, and we will show the output on that screen itself, our computer screen itself. Okay, so last time actually we connected some wire, LED, all these things. So today we no need to connect anything, any other additional things. So only the board is connected. Okay, so you know that board simply we can connect through the USB wire. Other than that, we will just we'll discuss the code and everything. So let me share my screen. So this UART we have already discussed in previous weeks. I think this is discussed in week 5 or maybe week 6. So this is used for the serial communication. Okay, so we have some hardware on the board that is called as a that use UART sometime, and that some many of the microcontroller countries use ART. Okay, USART. So the full form is Universal uh, Synchronous, that use ART, Universal Synchronous Asynchronous Receiver and Transmitter. Okay, and UART full form is Universal Asynchronous, that receiver and transmitter. So generally, most of the microcontroller contains this UART actually, and that hardware provide both the features, that synchronous and asynchronous. So meaning of the synchronous and asynchronous is synchronous means if we are transmitting any data, so we need the clock pulse also, that clocks pulse also with the data to just synchronize the data from transmitter to receiver. But here asynchronous mode, we send our data in the serial mode, that serially. So but we not send any clock with the data, and we send some identification bits like start bit, stop bit, to identify that what data is coming from the transmitter. And uh, one second. Okay, so that UART, so basically we send the data with the help of this start bit, stop bit, and that is the identification for the receiver, which data is starting from which bit. So when the data is start and when the data is stop. Sometimes some parity bit is also sent to just check the error detection and correction things. But normally we not used for demo purpose. So let's we will discuss this UART communication, and we will check this data, that data communication, how we can uh, send the data using this hardware. Okay, so I have this same QIDE. Okay, and my board is already connected. My board is Nucleo G474RE, some model. Okay, so G, basically G4 series. So that documentation of this is like this. So same, this one. So this is the series of my board, actually G4 series, and model may be different. So maybe you have another model, so just check the documentation when you are writing the code. If any you are writing any code, just check the documentation regarding the memory addresses, all this thing. So but we are using this G4 board, Nucleo. This is also a Nucleo series. So now I'll create one project, new project file. So I'll give the demo of that with the help of this HAL also. Okay, today that is actually very quick. So new project. Okay, new project STM32, and we will create this. Okay. So here, first thing we will select the board, and my board is the model Nucleo G. Okay, so G, that for this one. This is my model. So I'll select this and I'll create this next. And I'll give the name here. So like UART uh, underscore new board. Okay, so I'll create a empty project. Okay, if we want to configure this project with the help of that pin layout, all these things, and we want to solve this using HAL, so we will keep this option select target project type. So what is the select is the STM32 cube. So it provides the feature to configure all the things through the image, that the picture, and then we can easily do the complete configuration. Otherwise, if we want to start from the scratch, then we will select this empty option and then we will finish. Okay. So now I'm showing you. So this is the things. Okay, one second. Main.c. So this is the file which we need to check. Okay, this one. This is the empty file, or we can completely remove this. Just keep this as just remove comments and also remove this. Remove confusion. Okay, so also I'll just show you that which user pin we will use here. So let's create a new project to show the pin layout. Okay, so that I'm creating a new project, and this time you and STM32. The same things. We will select the board and so this is the board, and I've selected this. And next, after that, I'll give this name. So this is again UART, but this is second version. So new value using HTML. So I'm not selecting this empty option now, and we'll click on this finish button. So you can see it will create, it will open some another things. Some package is actually downloading, so it will take some time. Okay, just wait. Oh my god, 203 MB file is downloading. Okay, so here actually you can see this pin layout. Actually, this is a processor. Okay, and this is the pin of the processor. You can see this is given as a pin out view. And here we will select this user 2. So let's, yeah, we can't do anything. So we will select our user. There are multiple user option there, but by default uh, this board actually provides the communication on user 2. And when we select the user 2, when we enable the user 2, this PA2 and PA3, you can see this pin PA2, this will work as a transmitter, and PA3 pin will work as a receiver under the user 2. Okay, so we will configure in this way for user 2 our code. Not able to do anything. Skip 5 minutes. Okay, so only 50 MB data is remaining to download. So this actually QID updated sometimes when you opens after some days. So it's provide some update for the board and packages. Okay, so meanwhile, so how many of you are trying to these experiments on the board? Hello,
On. Yes, sir.
have you tried the previous experiments or any new experiments?
Yes, sir, I've tried, sir.
Okay, so all are working fine.
So I tried the previous two experiments on a nuclear board, L476RG board,
Mhm.
and I found that all the registers, everything is exactly the same as your board, sir. Even though it's a different board, I don't
Okay.
know the reason why it's the same register, but
No, one
it
thing
was.
actually, if you are using Nucleo series, okay,
Yes, sir.
and so they actually use most of the things similar.
I see.
for the same series. Okay, so that memory mapping, all these that registers address, they will keep all the things, most of the things same, but some features actually changes in the every model, some
Okay.
additional features. Otherwise these are the base things. So if you are using that memory address, so that address will remain same.
Yes, sir. It was
Similar
very,
for
your previous
yes.
lecture was very helpful. I was able to replicate it, sir. I do
Okay.
have some questions about it. Maybe later when you, then the Q&A time, I'll ask it, sir.
Okay, okay, sure. Yeah. So today we will also discuss these things. So every time what we are doing, we are just writing all these register address, looking, we are looking every time this register address. So what we can do better, okay, when we are creating any project or creating any application for any particular board. So some terms actually use as a driver. So we will discuss about this driver thing. So driver development today. So okay, so I think that is completed now. You can see, so inside this layout everything, all these categories are giving on the left panel, and you can select all these timers and that gpios, everything's are available here. So this pro hardware security related things, that analog adc, all the deck and system core, this you can see gpios are there. So all things you can select and configure the settings. So those things we have done previously, like selecting the bit and edit, select the mode, everything we can do manually from here. Okay, so here you can see, when I'm just moving this to this connectivity, so under this connectivity, this okay, why this is turn off here, this was not the previous. Okay, so we will check this. Maybe some update. This is disabled. Otherwise, you can see these are given UART 1, UART 2, UART 3. These are the total. And when we select this, so and when we enable this asynchronous, okay, I think some update it is disabled. Otherwise, if we select this UART 1, and when we select this asynchronous mode, so you can see some pin are actually enabled. Here the pins are selected PC4 and PC5. Okay, so this pins will work as a transmitter and receiver pin. Okay, same actually done for that user 2, and when we select this user 3, so some another pin will be selected. So for this you can see this one, PV11 and PV10, these two pins are actually enabled for the communication, that transmitter and receiver. So this RX and TX is decided that TX means transmitter, and this RX means receiver. So here you can select this, enable this by the manual things, and at the same time you can also set it, you can configure the setting. Okay, you can configure the second, you can set the baud rate, you can word length, with word length and parity bit, stop bits. You can set the configuration manually from here. And if you want to configure all the things from here, and what you can do, you can also start the that RCC for that. So you have to enable the RCC. So you can see where the RCC clock are coming. So computing CRC, multimedia is not there. Okay, RCC is also not here. After updating, it is changed actually. RCC time. Okay. Yeah, RCC is now here. Actually all the things are changed now. So you can enable the RCC, you can just high speed clock, you can enable crystal, that select the RCC mode, and you can enable the RCC. So in this way you can configure all the things, and after that, after configure these settings, you when you save this code, it will create a automatic code. You can see, do you want to generate the code? So when you click the yes button, so it will create a some other pre-configured code. Okay, where the all setting will be done in the code, and you can start your coding from the main function directly without configuring anything. So these things, uh, we will discuss the solution from this method also. Otherwise, we will discuss from the basic that another. Okay, so this is the another way using HAL. Otherwise, we will move to the previous one. So that is our code project. Okay. Now, so we have seen that that UART, we will use UART 2. Let's see that will work, because I have checked with the UART 1 and 3. So actually that was not working. Only with this board UART 2 was working previously. So because I'll check only with this UART 2.
Sir,
Hmm.
so you mentioned about RCC, sir. So for all these
Yes.
project, RCC is the default option, or is there some other option also available, sir? What actually I
No,
didn't
that our
understand the
board is
purpose of
actually
RCC.
provided internal RCC.
Okay, so I mean RC after choosing RCC, then we go look at all these timers, right? So I'm a little confused about the role of RCC and the timers, sir.
RCC means actually our that microcontroller board, where
Not sure if others are able to hear. I'm losing your voice.
Yeah, it's breaking actually. We're not able to hear.
Yeah, breaking, sir.
so
Breaking, sir. Voice is breaking,
RCC
sir.
is a hello. Am I audible?
Yes, sir. You're just audible, sir. But before that, we could not hear you. So I think there was some bandwidth network
Oh,
issue. I think.
oh.
No, we can hear you, sir. Oh, sir has dropped out. I think.
Hello.
Yes, sir, we are able to hear you.
Okay. I'm not sure what happened. Actually, it's completely system hang.
Maybe is it because of the software update, sir?
I'm not sure what happened. Yeah. Okay. So actually, what I was telling that regarding this RCC, na, so that this is a clock, okay, and it provides a that like a pulse sequence of pulse to the that controller. Okay, what happens actually to perform all the operations by the microcontroller, we need some that input. Okay, so for every pulse, actually, that some instructions performed by the microcontroller. So that pulse actually passes to the every part of the microcontroller. So initially, all parts are not actually enabled. Okay, so this RCC pulse are not reach every part of the microcontroller. So it is by default disabled for some part of the. This is because of saving the power. Okay,
Okay.
so when we want to enable everything, that means when we want to use some part of the microcontroller, like we want to use the port for the GPIO port to read and write something. So first we have to enable the clock for that part of the microcontroller. So at that part, that our pulse will be reached and operation will be start from that part.
Yes,
Okay,
sir.
if we are not using every part, so remaining parts will remain disabled, and it will save our power of the microcontroller. So because the purpose, most of the time our purpose of using this microcontroller is saving the power also, by
Okay.
performing all the operation with the less power, with the less power. So because of that, by default most of the parts are disabled, and this RCC are disabled, and if we want to use, then we enable that.
Sure. So when you share the STM cube screen, I have a
Mhm.
particular question related to that. I'll ask,
Okay,
sir.
okay, so
There is a particular screen where timers are there. I have a question on that, sir.
okay. And this board is also provide our internal RCC. That means some oscillators are there, some circuits are there that generate this sequence of pulse. So this is generated by the internally by the board itself, and board also provides some connection to that connect external oscillators to generate the pulse.
Right,
Okay,
sir.
so this clock. Yeah, so this
You
is
can just
ID. I think my ID is
so
now visible.
yes, sir. So now there is a. I mean, if you can go to that hall version of that page,
Okay, that version. Okay, so let me check.
I think that nuclear underscore hall. I think that
Okay,
that
this
one.
side, yeah, this one.
There is a
Okay.
page where you see
Ha,
the
ha, ha.
microcontroller, right? The pins you will be able to see. And there'll be a file called IOC or something like that, I think.
This is the file, but
Huh.
that is, yeah,
Yeah,
okay,
this
now
one.
okay.
So here there will be some place the clock configuration, the second tab, sir.
Kilo
Yeah.
configuration.
So the question that I had was, when we set up RCC, for example, whatever you're trying to do right now, so we enable a particular path, right? Is that what happens? For example, GPIO only this path is available, or does it work like that? What is the relationship between RCC and what we see here on this page, sir?
No, this is just showing the clock. Actually, in which part, what clock frequency we are getting. So this is the connection like this. So here you can see clock is generated like this HSC part. Okay, so what frequency it is generated, and all these are the connection through the every part of the board.
Right, sir.
Okay,
So
so
how do you
this
figure out
APB.
in this which part is applicable to the GPIO, sir?
How, so you have to see in this GPIO things. First thing, bus also. Every GPIO is connected through some bus.
The AH,
So yeah, that AHP1,
ABP. Yeah, you can
AHP2,
see it
yeah,
there. Yeah, on the
on
right
the
side
right side. Yeah,
near your
okay.
cursor. Yeah.
So you are getting this frequency 170 that megahertz. That frequency you are getting at this point, at
Oh,
this bus.
so which
Okay.
means, so I think that partially answered my question. Which means that if this ABP bus is what is dedicated there, we can't use anything else, right? Because it is connected to the bus, we have to use that only.
Yes, but there is some feature you can also change this frequency by I think. it is changed by here, but no, it is not changed. There is some way to, you can also change this, that frequencies,
I
megahertz.
think you earlier did it with that pre-scaler and all those
So
things,
this
right?
is the pre-scaler things, yeah. So you can set this, and you can see other
You can
next
see
one
it.
is,
It's changed already. Yeah.
yeah, changed. So you can change this also according to your use.
Got it, sir. You answered my
Yeah.
question. Thank you, sir.
Okay. Okay. So let's move to the main file. Okay. So we will use user three. Okay, that port, and we will use the that PA2 and PA3 pin. Okay, which is connected from that. Okay. Now it is not disable on this page, PA2, but let's check. We will also try the another. Okay, if it will not work. So this main C, first thing our work is to find out what are the required things. So first thing is the identify the addresses of all. Okay, so we need that bus. Actually, first thing we need enable the RCC for the this peripheral. So first thing we are using PA2 and PA3 pin, and these pin are GPIO pins. That means we need to enable the clock for that port A. Okay, and port A all these are connected through this AHV2 bus. So let's show you that memory maps things. Let's see this one. Okay, so here you can see GPIO is connected through this AHV2 bus. Okay, so that means we need to enable the clock for this AHV2, and we need also to enable the clock for UART, that UART. Okay, so that we will also identify that.
So,
Mhm.
small questions are here.
Yes, yes,
So,
ma'am.
when you're saying you enable it here, right? So, which
Hmm.
means that path right from the crystal oscillator to the to this entire path gets enabled, right?
Yes, yes, that path will be enabled. And no, that actually first thing we are identifying the base address of this AHV1, and
Yes.
inside this we will identify also that which part actually we want to enable. So that
But
we
the
will show
source
by
clock
the
is,
registers.
sorry, sir. So but the source clock is the crystal oscillator, right?
Mhm.
Okay, fine. Thank you, sir.
Yeah, you are getting the that clock pulse from the oscillators, but we can figure out that which part actually we want to enable. So that clock. So we will just do these things by with the help of registers. So, but we need to identify that what is the base address of this RCC HB2, where it is. These are actually connected. So first thing we need to identify the address of this. So you can see that APP1, this APP1 bus. Okay. So here this is the address APP1. We start, and this is the starting address of this 4000, and then this one. And GPIO2, we have already seen this above. GPIO is, this is the starting address. Okay, so we want to store this base address for our project. So first thing we will figure out that RCC clock for this. So RCC comes under the above part. So RCC is this one. Okay, and now we will move to the RCC in the page. This one, and see registers. Yeah, so GPIO you can see here that AHP1 bus peripheral, AHP1, or we need AHP2 peripheral. So this one, okay, and inside this you can see the port. This, so this is the base address. So what is the base address of this this AHP2? And after that, this is the offset value to identify the for this particular RCC. So we will add this, and inside this register we have this 32 bits where we need to set this GPIO1 enable to enable this. Okay, so first thing we will need, we will reach at this base address, and after that we will update this first value to 1 to that enable this RCC. Okay, so let's figure out the base address. So this is the offset 2C, and this is the HV2 peripheral reset. This is peripheral reset. I think this is also not correct. We have to search the peripheral enable registers. The peripheral clock enable registers. AHV1, AHV2 clock enable. This is the one. So 4C. Okay. So because we want to enable the clock for peripherals, so we need to check this one. Okay. And we will add this 4C value. First thing, we will add this 4C value in our base address to reach this register. After that, we will enable this GPIO A. Okay. So you can see we will pass the one value to enable this, otherwise 0. Okay. So this is the first thing, and same things we will do for that APB1 enable. So same things we will figure out that the base address for that. So APP1, yeah, this APP1 peripheral clock enable. This is not correct. So let me
17, I think. 17, 7417 maybe.
this one APV1 peripheral clock enable list. Yeah, correct this one. Okay, so this is 58. Okay, and this is the offset is 58. After that, you can see UART is coming here. Okay, so we need to enable this 17 pin to high mode, that one. Then our both clock will be started for port A, GPIO port A, as well as the that our user. So this thing is the first thing. So let's start the code.
Sir, small
Yes.
question, sir.
Mhm.
So what is the difference between 7417 and 7418, sir, in that thing? Because both of them are saying peripheral clock enable. One says register 1 and other says register 2 in the manual, sir.
Okay.
If you can just see the contents page of the manual, 7417 and 7418, they seem very similar titles. What's the difference between register 1 and register 2, sir? Is there anything that we need to look
Peripheral
at?
clock, APV1 peripheral clock, APV1 peripheral clock enable register 2. Okay. So access no wait state. Uh, when the peripheral clock is not active, the peripheral register read or write access is not supported. Here also. Okay, so this is depends on if that means if this part actually perform many functionality, so that is not performed by 32 bits actually. Okay,
Okay.
so there are many things connected to this bus.
Hmm.
Okay, APV1, so that's are not handled by these 32 bits of the one register. So because of that, another register is also there. Okay,
Oh, I
so
see.
you can see there are this is full approx
Fine, sir.
for
So,
some purpose. Okay.
so when we are looking at it ourselves, what criteria should we look for to select
So
one of this, sir?
actually, where your that particular part is coming, so you can see we need to figure out that to enable the RCC for user. So this is coming in inside this. Okay,
Oh,
it
oh,
is
got it.
not coming the another part another. Okay, this is the second actually register
Got it, sir. Got it,
that
sir. Thank
contains
you.
some other things. Okay, so we need to enable this one. So this the offset of this address is this 58. And first thing, let's over to the memory address once again. So RCC we need to check once again. So that RCC part. Yeah, RCC base address is this one. So this is the base address of RCC. We will add offset in this value. Okay. So let's note down all these things, and then we will write these things. So first thing, we will define the all address actually. Okay, so has defined that. So we will use the macro for that. So inside the not the main function, we will define this macros outside of the function. So these things actually we do every time. So what we will do in the next part after this, we will understand that the structure of the project, what we should do. So this is very difficult to identify every time this register address, all these things. So he has defined, and we will give some name for our that RCC clock. Okay, so that RCC, let's we want to enable the RCC for AHB2. Okay, so that AHB2, and this is enable. Okay, so that we can give the name enable registers. So that and we will just pass the memory address for that. What is the base address for this? So we have seen this base address here. So this is the base address. We'll copy this, and we will write here. Okay, so this will not be written like this. So SCC register. Okay, so we will mention what type of data this actually is storing. So this register contain the 32 bits. So we will mention this by the typecasting, and this space will also not come, and here 0 is also there, 0. And before that we have to do typecasting. So typecasting, we will give the typecasting uint int 32, okay, and underscore t, and this is asterisk. So that means this is a pointer, we are doing the typecasting, and overall value we will pass as a this is also a, yeah. So what we are doing, this is the address value, okay, of some locations, and we are storing this address into some, we are considering this as a pointer, okay, and pointer contain the address. So but we have to tell to the compiler that what type of pointer we are storing. So that means this address contains some integer value, 32 bits integer value. So that pointer address is representing. Okay, so because of that we are typecasting it. What is this type, what is this value representing actually? So this is representing a address of integer type, okay, value. So because of that we are doing this typecasting.
Sir,
Hmm.
so here you've written RCC underscore AHB2, but RCC is in one, sir. Is there a reason why you put two?
No,
RCC.
RCC, then AHB 2 bus. This is for the GPIO port.
Oh, okay, got
Okay,
it,
so
sir.
we can give any name. Okay, just for our indication.
Got
Okay,
it, sir.
so
Thank you.
that means we want to find out the address of RCC clock of AHB2 bus to enable. So that Ayana, you can write anything, okay, which you can understand.
Fine, fine, sir.
Okay, so this is the base address of this, but we want to find out the exact address of this register. So that means we will add the offset value. Okay, so we will add the offset value of this GPI port A. So that registers you can see here. So AHP1 peripheral enable. So then we will figure out this. Uh, yeah, this one AHP1, AHP2. Yeah, this one you can see. Okay, so what is the offset of this 4C? So that means we will add this offset value into the base address, then you will reach at the final this RCC, and after that you need to enable this value 1. Okay, so we will add this value 4C into the register. So this here last these things we will add 4C. Okay, now this is pointing to the RCC for our GPIO port A. Okay, now this is the first. Similarly, we will do for the another RCC, that is for user. So that is APB1. Okay, so APB1. So remove 2, and then what is the base address of this? So base address is same, and that offset value was 58. Okay, so we will add this 58 here. So like this we will add assign the registers. So this is the first thing for the RCC for the both part which we want to touch. And another thing is we are now in the port, actually GPIO port. So we are using two pins, port A, port 2 and pin 3. Okay, so we need to enable the mode for, so what is the purpose we want to use for the port actually. So we are using some that transmission and receiver things. So we have to enable these things, we have to enable the mode for that, which mode actually we want to use, and also we have to set the value for that. Okay, so first thing we will identify the address of GPIO mode. So has define, and this is actually registers. Okay, so after GPIO mode register, so that GPIO and mode A. So because this is a port, and let's write GPIO A here. Okay, so GPIO A, or we can so mode and register. This is representing a register. So same things we will figure out that what is the address of that. Okay, so we will just move to the document, and here inside the, now we will move to the GPIOs. Okay, GPIO section, and inside this GPIO section you can see this is the GPIO port mode registers. This is the first register. Okay, and the offset value is 00. This is the offset value, but what is the GPIO port A? Actually the starting address, so that we can see from the memory. So that you can see GPIO A starting address is this one. Okay, so this address is also representing a port mode register, so that we will use directly here. Okay, so that means we will write this here and remove this, and before that we will put this. Okay, so now this is mode register, because offset is also 00. If we add the 00 in this, so this will remain same. And after that, inside this register we need to select the the what is the purpose of this. Okay, so this means here. Okay, so we want to use this as a input mode, general purpose mode, alternate function mode, or analog mode. So regarding this user communication, that transmission and receiver, we select this as a alternate function mode. Okay, so that means we want to set this 10 value to our mode, that pin actually. Okay, which pin we want to use. So this mode 0 mode, this is representing a one pin. So how many ports we have? So we want to use P port 0. Okay, so this is representing a that PA0 pin. This is representing PA1 pin. This is representing PA2. Okay, this port A second pin. So we will set our pin here. So that means we want to use our both pin 2 and 3 for the alternate function. This alternate function. So that means this 10 should be set at this place, mode 2 and mode 3. Okay. So because of that, we are just storing this base address. Later we will store a 1010 value at the both place. Now we need to find out the alternate function. So that is actually we will use the next register. So that is GPA 8, not here. Set the set output. Okay, this is coming later. Yeah, this is alternate function. Okay, so this alternate function we are selecting above. We want to use that pins for the alternate function, and you can see X is coming from A to G. So this is representing the port, and offset value is this 20. So that means in to set this value GPIO alternate function, we will add this offset 20 value into the base address of the port A register, and after that we will set our some value inside the lower in this register value. So that we will set regarding for this operation, that user operation, we select this AF7 mode at 0111. This value we will set at that place. Okay, so this is the things we need to do. So we need to find out this register value. So this is the first value mode register, and second value we will use for the alternate function register. So that means GPIO mode A, then alternate function the register and low. So we have selected this A, F, R, N. Okay. So this is representing 20 offset. So we will add 20 here. Okay. Other things will remain same. Okay. So this is the base address of port mode register. This is the base address of that alternate function mode. So these are the two things we need to enable the things. Okay. So that we need to initialize. So first things we can start the things. So what we will do, we will just write some function to enable all these things. So GPIO init. So we can create a separate function for that. So that means we can write a function. So we can write a function like void. So capital, sorry, void. Okay, GPIO that init. Okay, so we want to initialize this. Okay, and just keep empty this. And similarly, we will write RCC clock that or RCC init. So this RCC init is also just enable the clock. Okay, so two function I've defined, this GPIO init and RCC init. So what we will do, we will initialize this init function. So inside the GPIO init, uh, we have this. Okay, so the GPIO unit, RCC unit. One more important things: if you are doing some operation on any GPIO port or anything, so your RCC should be enabled first. Okay, so I am writing two function here to enable the RCC first, and then GPIO also initialization. But this RCC operation should be called first. Otherwise, your above operation will not be performed. Okay, so if you want to set something, set some bit for the register on the GPIO port, that will not be performed if your RCC is not enabled. Okay, so first things you have to enable your RCC, then you can only uh, update the another part. Okay, so here, one second. So first thing, we have to enable the clock. Okay, so to enable the clock, what you need to do, you need to just take this inside the RCC, and you need to set the that first bit. Okay, so first bit you need to set, and this is a simple or operation we can use. We have already seen many times this. To set the first bit, you need to write like this: 1 and 0. Okay, so what we are doing, okay, so what is this? Okay, what we need to do? Syntax error plus two. What is the syntax error in this?
So that pointer should be inside the brackets, sir.
Hmm. Yeah, please open your mic if someone is raising their hand.
Sir, I've just put it in the chat. This is how you've used it in your previous code, sir.
Okay, okay. Only int. Okay, so this time I am using
No, the
u
pointer
int.
was inside the braces, the brackets.
Okay, that. Okay, okay. So let me check.
I've just copied from the code that you posted in Discourse.
So this pointer is inside the bracket, no?
That, yeah, now it is correct, sir. I think earlier it was outside.
But it's still, this one is also looking. Okay, so but still it is showing some syntax error. Okay, okay. So that we are actually using this function and we have defined this RCC. This should be working. Okay, and let's write this inside the main function. Any naming difference? Okay, I'm writing the code first. Okay, then we'll check what is there. I think we were missing something small. Okay, another registers we have this RCC, this one. That this one, and we will note out this. But this was the 17 actually 17th bit we need to do. So we will shift our 17th location.
Should the semicolon be removed, sir,
This one.
after define?
Uh,
Does it make a difference?
no, no. I think some space there it is creating a problem. What mistake we are doing? RCC HV to enable. So this is the typecasting of U in 32T, and we have already declared this. And this is let's missing colon. Okay, this now error. So this error. But now it's okay. So we are writing in the same way now. The previous one. Now this is okay. Let's use the int int. Oh
Sir, is a space required between the int and the pointer, sir?
Sir,
no,
the
there's no
semicolon at
space.
the end, sir.
Sorry.
For hash define, no semicolon, sir, at the end.
This should not be there.
Yes, sir.
Yeah, in your previous code you have not used. No, is there a space required between int and that pointer here? That does it look for the space?
No,
I-
there's
I-
no space
no,
actually.
no, no. Integer pointer
Here.
that no next to that after the int. Is it
Uh,
required? Is it looking for that space or something?
no, nothing.
Should not.
Okay, let's take a that code copy. One second. We have written like this. I am missing something. Uh, if you have complete code, can you just send the complete line?
Yes, sir. I'll just do that, sir.
I don't know what we are
Um,
missing.
I'll just copy it from that
Yeah, now
push.
it is removed. Okay. I copied your code. So this is a small x. What is the change? Okay, double bracket is, oh, okay. Oh, we are using some additional bracket actually. Okay, now it is removed. Okay, so actually, regarding this typecasting, so we are using this, and before that we are using the typecasting. So this is the one value, and after that we are considering that this is a pointer. Okay, so this asterisk is representing that this value will be represented as a pointer. So this is the typecasting first to the address, and then this will, because this is a macro. This is not a variable. Okay. So what we will do when we are using these things, so it will use as a value of this address. So this is the dereferencing thing.
So
So what is the
if you
hmm.
use u int 32, will it work, sir? Now that this correction is
That
done.
it will work. Yeah. U int and 32 underscore t. Now it is working. So that was some bracket issue. Okay. So now it is working. So this, when we are writing this, now the clocks are enabled for port A. Okay, so this is for port A, and we are setting the first bit. Okay, so this is the address. So here, this, when we are writing this RCC, this one, so this is referring to the register values actually. So what are the 32 bits value we have? And for that value we are updating the first bit. Okay, so that means 1, that means we have the value 00001, and we are using only 0 left shift, so that means it will remain same, and we are performing the OR operation with the actual that registered value. So OR operation will perform with the first bit, so that one will, this is the one bit, and overall bit, first bit will become a 1 after this OR operation. So that means first bit will be the set to the 1. So our RCC will be enabled by this, and same things, this US USART, actually we have seen that register. So that user 2 are coming, is coming at the 17th bit position. So that we are enabling this, we are shifting our 1 to the 17th index from the right, and then we are enabling that as a 1. So this is the two operation to require to enable the RCC for both. Now similarly we will set our uh, that GPIO. Okay, so all GPIO will set. So here first things, we need to enable this GPIO mode. Okay, and our port is that GPIO port A. Okay, so what we need to do, so first we will need to set our GPIO mode, that GPIO mode, both both pin. Okay, so pin number 2 and pin number 3 to the alternate function mode. So how we can do this? So we can write here, so GPIO mode R. Okay, so this is the GPIO mode. First things, we will clear the bit. This is also a good practice. Before setting the bits, clear the bits. Okay, so and to clear the bits, we use this AND operation, AND equal to, and we will use inside this, so that GPIO mode register. So these things, how many? Okay, 2 3. Okay, so to clear, so we want to make both bit 00. So if you know, if you remember the register, that, so GPIO register, this one. Okay, so each mode actually require 2 bits, and this should be set to 10, and we want to set this this one. Okay, so that means 0 1 2 3 4. From fourth bit and fifth bit should be set to 10. Same 7 and 6 bit we should be set to 10, but before that we will set to 00 to this, and same 00 to this. After that we will set only the 7th bit one and 5th bit one, so that will be set to the 1010. Okay, so to clear this, what we will do, we will just perform the AND operation with 00 at this position. Okay, AND operation with 00 this position. Okay, this one. So to perform the AND operation, we will perform this. So 1 1 is represented as a 3 number. So 3 is the representation of 1 1. And how many bits we need to shift? We need to shift 4 bit to this. So that means we will write 4 here. Okay. So we have 1 1. Okay, that complete 1 1 part will be shifted 4 times to the left by this operation. But this is 1 1. We need to just change invert this. Okay, so we need to invert this. We will use the invert operation, and this is the one operation that will actually that set that 2 bits to 0 0. So if is it not clear, I'll explain this. Is it clear to everyone? So how we are actually clearing the bits and what this operation is actually.
Sir, please explain again.
So this is 1 1, and that 1 1 will come at the 5 and 4 position, and then we will invert the complete number. So that will become a 0 0, and all remaining bit will become a 1 1. And then we are performing AND operation. So corresponding 0 0 bit will become a 0 0. So this is for first pin number 2, and same things we will do with next pin number 3. So that time we will use the 6. Okay, so these two operations are to clear the bits for that. After that we will set the bit. Okay, so to set this bits to that means fifth bit and seventh bit to 1. So what we will do, 1 0. Okay, so that means we can write the same operation as previous. So now OR operation, that OR operation, and this time we will shift our, this is not required now, and now 1 0. So 1 0 is represented by 2. Okay, so 2 corresponding binary value is 1 0, and 1 0 we will shift by 4 position. So corresponding OR value will become a 1 0 mode, and same things we will do with the another value. So at that time we will shift this to 6. Okay, so that means we have cleared the bit, and now we set the our both pin to alternate function mode. So this is the GPIO one first part, and second part is we want to set that our alternate function registers to AF7 mode, AF7 value. So that is actually 0 1 1 1. So that, so for same things we will do, we will perform the clear operation first, because we want to set here 4 bits. Okay, so we will clear 4 bit also again. So now the register name is that GPIO AFRL. So that is this is the alternate function. So same things we will do similar to this one. Okay, to clear the bits, but here we need to move. So this is the second pin, so that means we need to move to second pin. Okay, so here we will move to first and second. Okay, so last time we did 2 into 2, so this time we will move 4 into 2, so this will become 8. Okay, so because the first pin is referring to the 4 bit, so that 4 bit 0 1 2 3. Second, that one index pin is referring to the that next 4 bit. So in this way we are moving our value. So this 3 will become, we need to set here that 15. Okay, so 15. So 15 corresponding value is 1 1 1 1. Okay, so 4 times 1, and that 4 times 1 will become a 4 times 0, and corresponding 4 bit will become a 0 for that by this AND operation. And now the same things we will change, clear the another bit, and this time we will add 4 3 is 12. So that we will move shift the same things 3 times to the registers, and this is the clearing the registers, and after that we will do the same process to set the register. To set the registers we need OR operation. Sorry, this is this one. Okay, and here what we need to do, so this is 8, this is 8, and now we need to set 0 1 1 1. So that 1 1 1 is representing to 7. So here we need to write 7. Okay, and now the same things we will do for the another pin, third pin, and that time 12. Okay, so now that is our GPIO initialization. So this function is now doing GPIO initialization and setting the that both pin to the correct mode. So now two part is done, and from our main function, this is the first call we need to do, and we will call this as a first to enable the clock, and second, this is the second we will call this one. Okay, so this two function we called. Now our clock will be enabled and our GPIO will be set. Now the next part is the UART this things. Okay, we need to set initialize our UART. Okay, or UART, because we are using this UART as a UART only asynchronous mode. Okay, so we will also define one function for UART in it. Okay, so that we can write UART also. We can give any name. So sorry, void and UART. So okay, we are using only for asynchronous mode. So UART and init, and that same things. But before that, we need to identify the addresses for that also. Okay, so that UART2 base addresses, what is the base address for UART2, and some that registers we need to set here. So what are that registers actually? So first things we will move to the document. So and we will see where the UART2 base, what is the base address, and then see. So first thing, same memory. So this is the base address. Okay, so I'm noting down this. Now you, and then this is 2. That, so here we will just note down the first register. So that first value is based on the address. We will just mention the name, and this will remain same. Correct. Okay, so now this base address. Okay, so we need, yeah, I have noted down this. So this is the base address for UART2, and now move to the registers. So that what registers we need here to initialize for the, that UART enable. Okay, so here, so first things we move to the register space. So this is the base address inside the user. So let's check.
37.8, I think, sir. The link is there in this page.
37. This
The
one,
link
yeah.
is there in this right side, sir.
Yeah, okay. So inside this, we need to check user registers. So these are the registers we have. Okay. So these are control register, and we have another register. So also baud rate register we need to set. Okay, control register. And what is the offset value for the first?
00.
Okay, that is 0, 0. Okay. And another registers we have. Control register 1, this is also same. Control register 2. Oh, there are lots of things actually. Control register 3. Yeah, this is baud rate registers. This we need actually to set our baud rate. So user underscore BRR. and what is the offset for this is 0C. Okay, so this 0C we need require. So here we will do that means we will add 0C so that it will become a 0C, and we mention here this is a baud rate, so BRR. Okay, and we also need this control registers. So this is to enable the things. So let's this is the second one. Okay, so that's control register one. So CR. There are multiple control registers. So let's see. CR2 and CR1. CR1. This PX and RX receiver. So that transmission and receiver things. So that pins are that bits are coming here. Okay, so TE you can see T transmission register receiver RE. All are coming inside this that control register one. Okay, so we will use this. So this base offset value is 0 0. So now just keep this as a 0 0 0 as a base address. So this is CR1. Okay, apart from that we also need that start wait and all some other registers also. So that is actually a total. So this actually all these registers are representing to the same configuration which we have seen using the HAL. So some value we need to set here. So that next is that I move to the next register. So this control baud rate. Okay, so this is this timeout is not required. Request registers. So because yeah, transmission data registers and receiver data register we need. So that is our purpose here. That is also not there. Interrupt flag. Yeah, so this is the one. Receive data register, because this is the registers where our data will store during the transmission, and so data will receive from some registers and data will be write some registers. Okay, so this is receive data registers. So where data is coming from the transmitter and it will store at the receiver. So these two registers we need, that receive data registers and this TDR, okay, transmit data registers. So where our data will be stored. So that 24 and 28. So these two value we need. So this is RDR and TDR. So first thing RDR and next is TDR. Okay, so this is transmission data register. And now the offset. Okay, so that offset we need to check. This is 24 for the RDR and 20 for that. So 24. So this will be add in the base address 4400 24, and this will become a 28. Okay, and apart from that we need one more, that yes
Sir, you just change the last two digits, sir. Should it be added or we just overwrite it like this, sir?
no, we are adding, because that is also a that hexadecimal value. So if we add this hexadecimal to hexadecimal, that will be the you will get the same value.
It was C, isn't it, sir, earlier?
So no, this was the this one. This is the base value for actually. Okay,
Oh, I
and
see.
we are
Got it.
adding in this base value
Got it, sir. Thank you.
offset. And one more is that set. I will get to check. So 14, 15. How many registers are there? Okay, not changed. There is one ISR is also there, so that we also need PDR, RDR, ICR. Okay, this one interrupt and state arrest ISR. This one, so 1C. So we need this. This is regarding some acknowledgement, or this is also related to this transmission and these things. Okay. So that we need 1C ISR. So these five registers we require to set initialize our UART. So this is 1C, 1C, and this is ISR. Okay. Now these five registers we need required to configure our that user that pin. Okay. So this will all value will be set inside this uh, function we have created here. So this init. Okay. So now we will set this all the init things. So first things we need to set our baud rate. We have to enable the that clock. We have already enabled the clock, but we need to set the baud rate, and we also need to set our the transmitter, receiver, and user to. We need to enable all these things. Okay, so to set our baud rate, so we need our baud rate register. So that is actually BRR. So this one. Okay, so here actually we can set this baud rate to, by default it is set to 115200 value. Okay, and so we can set to the same value, or we can also change the value. So to set the value, so we generally write like this, that what default the frequency we have 1600, so 16 megahertz, so 6 times 0. Okay, and divide by, so that baud rate 115200.
So how did you pick the 16 megahertz, sir?
By default this is the default value as a input clock frequency we are achieving there.
Is
Okay.
it because of this board, sir?
No, we are setting our baud rate this for
Okay.
our user, but this is the by default value as a clock frequency for this.
Nice.
Okay, so if we want to set our baud rate means here, so during the serial transmission, okay, so how many bits we want to send in 1 second. Okay, so that represent by a baud rate.
So this
So
16 million is the default number you have to give for any baud rate, or it will change for the different baud rate?
no, we are setting our baud rate to 115200. You can also
No,
set. Hmm.
suppose I am keeping 1850, 9850. In that case, what will be the first
No,
number?
the above number will remain same. You need
Okay,
to just put here 9600.
okay, understand.
Okay,
Yeah.
so this is representing the baud rate value when we are writing the lower value.
Okay.
Okay, so what syntax error is coming now?
I think this bracket is missing. I think. Okay.
Okay, so this is the one thing baud rate we have set, and we have enabled our that another things. Okay, so that we have to enable control registers. Okay, so you CR1. So in the same register CR1 we will set our all values. So we need to set that RETE and one UE bit. So CR1 registers we have. So like control registers. What is here? BRR. These are control register 2 and 3. Yeah, so here we need to set our that first bit UE, okay, and that RE, and this, so this TE. These 3 bit we need to set to 1 actually. Okay, so you can just leave the value purpose over the all things. So, but this is just to enable our user 2, so that U is representing user enable, and the T is representing transmitter enable, and RE is representing receiver enable. Because all these operation will be performed, transmission and receiver will be performed by the user. So all these 3 bit need to set. Okay, so you can write to set function here, so that CR1, so that registers you need here. And this is or operation equal to. So to set UE, so you need only this 1 and left shift 0. Okay, so now just this is the 1. And to set second value, you can write so that you need to set 0th bit and second and third. Okay, so here just move to 2, and next is third, so this is 3. So all these 3 value will be enabled. Okay, so now these are the 2 basics we need to update here. After that, yeah, so another registers actually we required for this receiver data register, transmit data registers required to read or write the data. Okay, and I think ICR, yeah, ICR we need to check that our flag is set to or not, because this data is sent in the serial manner, and we are getting that one start bit and one stop bit. Okay, so start bit is just a low bit, 0 bit in the for that the data format. If you remember the lecture, that week 5 content, so start bit in general, this mode our that clocks actually, if there is no data transmission, then our mode will remain high. If any low bits come, that is the indication for the start bit. And after that, after sending the particular bits, if you are getting the high bit, then that is the representation for the stop bit. So actually this ISR is representing to identify the stop bit and start bit. Okay, so when you are getting the new data actually, so you can identify this information from this registers, ISR registers. At any point you are getting this start bit, so that means your transmission, that reading will work will be started. So that means you got the start bit, your data is coming. So you that you are actually will start the receiving operation. Okay, so this register is required for that. Okay, so that we will check these 3 value inside our function when when we will send our data. Okay, so now
So
these,
it will be dynamically set, isn't it, sir? When you want to send it, you set it and reset it, these things.
so actually from this registers we will read the data. This TDR we will write the data, and here we will check some 1 bit when our data is coming actually or not. Okay, we are receiving any start bit or not. Okay,
Okay.
and after getting our start bit information, then we will start our reading and writing process. So that is actually required. Okay, so that means now this initialization is only these things that use art. These pins are required. Now we will call this function also from main function. Okay, so now this will be set. Now we need to write another function, send. Okay, send characters. So now the main function is start from send character, and that is will write here. So that void UART and then send at, okay. and we are sending the character, so we need one character here. So that here, and see, I'm taking some variable. So this is the function to send the character to the UART, and after that we will write the definition for this. So that is actually yeah. So here actually we need to check our flag is set to or not. So we will write one condition here. So while first thing we are checking user ISR register here. So if this is not true condition, okay, so that you that what was the register name? ISR this okay, this ISR value, and we will check the some particular bit for that. So that we will check from the register. So the ISR register. Okay, so this is here. There is the interrupt. This
It's
one,
the next one, sir.
yeah, this
Is
one.
it- oh,
ISR, yeah, correct. Okay, so here actually we need to check the so this bit actually we need to check receiver actually information RXFNE. So that RXFNE bit number it is not given. Actually this is just provide the indication that one start bit is actually received. Okay, so this bit we need to check what is this bit corresponding. If you are getting start bit at this point, you will start receiving the data. Okay, at this point if you are getting the stop bit, you will stop receiving the data. So this is for no, so this is we are sending the things. Okay, so this is not the, yeah, this is for receiving information, but we are only sending the data. So we need to check this TXFNP. Okay, so one new character we will send when actually our previous data is already completed, stopped. Okay, then we will send our new data. So we need to check if previous value is now completed. So that things we will check from this bit, seventh bit. And another side, this RFX, this is for receiver side. So receiver will check if the start bit is coming now, so that will start reading. So we need to set the seven. We need to check 7 bit, and inside the code this while loop, and we will perform to check the bit. Actually, here we are not setting the bit; we are checking the bit. Okay, so what is the actual bit at that point? So we will use AND operation. Okay, and AND operation on this seventh bit. So that is the way to check the seventh bit. And if yeah, this okay, so, yeah. So this is the while loop we are running. Yeah, the user this pin is actually not set. Okay, so if this condition is true, then not set. Yeah, okay, so not received. Hmm, okay, yeah, so this is actually empty loop. This will run empty if there's no bits are, that means previous data is actually sending. Okay, so if this is indicating that lower side, this is not true, this bit is not set. Okay, so this is identification that if this bit is set, that then we will identify that our data is that previous data is completed, and we will send the new data. So otherwise this loop will remain continuously running. Okay, if any previous data is now completing or maybe transferring. Okay, so this loop will run, and after breaking this loop, we will send our data. So that data actually we will write like this. So the TDR. Okay, so we have the transmission data registers. This one. Okay, And then after completion of this loop, if already data is sending, then this loop will running. Okay, and once the data is completed, then this loop will break, and we will set our next character. We will set our next character to the registers. Okay, so C is representing a character, and now in registers we are storing this new character. Okay, so which we are receiving from this function. Okay, so this is the function to send character, and in this way we will send the data. So now from the main function we will call this, and we will send some data here, and we will initialize some data also. So like that main function we will move. So where is the main function? Oh, the main is above. This is while loop. This is now okay. This is ending. I'm just writing from the above. So now here inside the main function, we will just write some that strings. Okay, so I am writing some strings message. So like uh, we are creating one array. Okay, so that we can write like this care that str, and we have some the size for that like 30, and we are passing some message. Okay, so like hello, this is embedded C programming. I'm not sure this is the higher length. Let's increase this scale. Okay. So this is just a string array, and we have the value for this. We have assigned some message string for that, and after getting this, we will run a while loop. So inside the while loop, so we know that when we are writing, we want to perform anything from the embedded controller. So we run the code inside the while loop, so that this while loop will run infinitely. Okay, so this is not required. And also we will write a return statement, but it will not execute anytime. Okay, so we sum. So now inside this while loop, we will send our data. We will send our data. So that means we will run a loop. So for, and we will send our data character by character. So for, and we have now int I equal to 0, and here I equal to 0, then I is less than equal to. So what is our that strings? So this size of this str. Okay. So we will write this I is less than size of str. Okay, and now then I plus plus. So we are reading character by character, and inside this for loop we will call our function that UART send characters. So this one, and inside this we will pass this. So this character, at the place of character we will pass our that str and I. This is an array, so we will pass our array characters. So we are passing, we are sending character one by one, and after sending the complete strings. Okay, so this sending after sending this complete strings, we will give some delay inside this. Okay, so now we will give some delay. So delay, I'm calling the functions like this. So delay 1000, but it will not work like this. We have to define this function also. So so that means after sending this one line, it will take some break, and then we'll start sending again. Okay, so now define one more function delay. So void delay, and it will take some integer value. So like int n, and then yeah. So for regarding the delay operation, you can perform you can run a loop, or you can do any type of loop you can run. Okay, so like you can run a while loop. So while you have okay, so while you can run like this delay. delay. That is,
We can use timer also, no, in this.
you can also use the timer, but then you have to define all the timers registers to use the timer. So the previous session we use the PWM, no? So at that time we use the timer. So same things you can also use the timer for the delay. Otherwise you can create this delay using the that some loop. So delay minus minus like this. So minus minus, sorry, minus minus. You can perform this operation, and if your delay is like greater than 0, okay. So suppose we are getting 1000 value from the function, and if this delay is greater than 0, then we are decrementing this. So that 1000 to 0, it will come, and after that, this loop will be breaked. So in this way, you can run a loop for the delay. Yeah. So I hope this is completed now. So for the transmission,
I think the delay function you have to use n, na, instead of delay minus minus.
yeah, correct. Sorry. And yeah. Okay. Yeah, so this is done. Transmission is done. Send character we are sending. Return 0. This is the hello part. Okay. So now regarding the output actually. Okay. So what we need to do? So we will check the output on the terminal. So we need some that serial terminal for that. So I have some. There are many serial terminal where you can just read the data. Okay, so from the serial data, and that board actually provide this return data on some port actually. So when you open the device manager of your device setting, so like I'm opening the device manager. So our board is actually connected through some that port. Okay, that, so you can see when I'm opening this device manager. So these are the ports actually where our connections are there. Oh, our board is now not connected. One second. And when my computer was hanging, actually I removed this. Okay, now you can see this our STM this STM micro electronics ST links virtual. Okay, so this ST links is now connected to our COM port COM6. Okay, so now we need one that serial terminal that you can download. Any one is putty PUTTY, one is Tera term. There are many terminals are there. So I have two. So I am
Uh, just one
yes.
question. In case if you want to write some terminal like Terra and Putty, a very small terminal using the VS Code or C++, what is the minimum requirement do you need to understand here?
Minimum required means.
I mean, suppose I want to write a driver to read this serial port using the C++ or some other package. So, I mean, we can do that also.
Yeah, you can do, because this is just reading the data from some port actually. So you
Okay.
can perform this operation by any of the terminal.
Okay.
Okay, so here, so this setting we need to do check here. So this is TCP protocol that port, and serial we need to click on the serial. Okay, so serial port, and we need to select our board connect that COM. Okay, so COM6. Okay, after that, okay. So now we have another terminal that this is the that there are this is the terminal. Okay, but we need to set this to the setting. So this you can see COM6, but now our baud rate is set to 9600. So we need to change this to 115200. So, and remaining bits will remain same. So 8 bit, parity is none, stop bit is 1 bit. So all these things are fine. Okay, now this is the terminal that we are checking, so for the data, and now we will run our code and we will upload that code on the board. So this is build project. So some error we are getting, so let's see what error we are getting here. So This value. Change and so not equal to this one. That's right. So this parameter of parent will not change into these things we need to change. So this is a loop actually. This okay, so while loop not to use our ISR value and this. So we're getting the correct. Okay, so let's again. Now this is what. Okay. So after reading the value action, then we are checking. Okay, like this not symbol. So now our build is successful, and then we will run is on the board. So this is the first time. So we'll keep the setting same. Or they will check some setting. Yeah, this is fine. Oh, I think yeah, this is coming very fast actually. So we have to increase our delay. Okay, so let's update the code. Uh, okay, so where is the delay? This one. So let's increase this 6 times. Okay. Now it is coming slowly, but we are getting into the same line. So we can just pass some new character here, and that one more character we need to properly coming. So that is R actually. So build project. Yeah, STM. So I'm removing this clear screen. Now this is coming line by line. Okay, so you can see we are getting this data from the serial input. Okay, we are sending from our this code, so this loop is running, and this is sending this complete line. After that, one break, and then again this while loop is running. So in serial input, we are getting this message. Okay, so this is one way to that check the UART functionality. Okay. So you can use any terminal. So I have another terminal also. So after stopping this, we can check that also. Putty and some more are there. So I have only used this. Okay. So this is the one thing we have write the code completely from the registered level, everything. Now another thing is you can do the all things by that another way. So I'm stopping this. Okay. So that is actually very small code. Okay, so regarding this, okay, HAL, okay. So when I click on this page, so here we can configure this. So let me try to configure. This is not enabled now. I don't know why this is disabled. So first thing is RCC. We have to enable the RCC so that like Okay, so we have already done enable this. And another thing is connectivity. Inside this connectivity, we need to configure this, but now this is disabled. So let's select another one. So I'm removing this disable. Okay, so only user one I'm using. So the pin is actually PC4 and PC5. Okay, so these are the two pin. And after that, when we save this code, so we will get to generate code. So when we click on this generate code, it will create a code for us. Okay, so now it is created, and inside this code, you can see this handler name is given that handler type is HUART1 because we have selected UAR that UART1. Okay, so this name is coming here, and some all the configuration setting is done by default. So then you can see this clock and RCC clock and GPIO corresponding all are actually configured, and we need to write the code inside the main function, and that inside the this while loop. Okay, so this while loop you can see this is empty, so we need to write our code here only. Okay, so here we will use one function that HAL, that is slash and transmit, no sorry, UART. So by control space, yeah, we will get this. So UART then transmit. That's hmm. So this is the function we can directly use like this. And first thing we will pass the value because this is now created a variable. So that, and here we will send our data. So as the previous example in the main function, we define this line. So this line we can create here. So this is the hail. This one. Okay, so we can define this globally. We can define. Okay, so we for the main function. So like this is str50. Okay, and we can use this inside the here. So str. Okay, size of we will calculate. So size of str, and this is time out we set. So generally we set like 10 or 100. We can set anything. So this is the one. Okay, and after that we will pass some delay here. So that HAL underscore delay, that function we have directly. So that we will call this function, and we will pass some delay 1000. So this 1000 millisecond is 1 second. So that is required. Okay, so this is the only code we need to write if we are configuring like this, and we can also upload this code and we can check it is working or not. So build project.
Sir,
Yes.
from the HAL code,
Hmm.
we will not be able to export it to the register level code or something like that.
Yes, yes. So actually, this is a mediator level actually between user and the hardware. So it is just a like as a API where all the functions and everything is defined by some names. You can directly call the names and you can directly perform the operations. Okay. So like this function is defined, HAL UART transmit, this function is defined. So this is similar to your API, application programming interface. You are just passing the value and all the operation will be done, which is already defined in some other files, which is actually where from we are using this function. Okay,
But can it export to a even lower level code through this? For example, export to a register level code from here.
you can write that code also. This is simple C file. Okay, so this is same source main.c file. You can write that code also here.
No, no. Does it automatically export? Let's say if you want to export this HAL code, does it do it or we have to manually do it?
Okay, so from this file you want to export that that register label code.
Can
You
we
are
get
saying.
me extract it from here automatically, or
I think you cannot generate that direct code, but yeah, all files are available inside this driver, all these things. So yeah, that actually I wanted to. You can see this HL drivers also are created inside here. All
oh,
file is there. So this is also this HAL is have also created the driver files for the complete that memory, that peripherals all separately.
I see.
Okay, and all are links actually. You are only calling this function, and it is connected through the HAL libraries, and you are getting all the information through that. So that is called as a driver development. You can also create this driver.
Okay, sir.
Okay, so this is created by the STM, but you can also create your own driver. So like this function name, you can also create your function name. You can create the first your header file and source file, and you can directly call your functions and perform the operation. So that is one-time work actually. So if you develop the driver for any particular microcontroller, that is only the one-time work. After that, you can use multiple times. So that is called as a driver development. So let me just run this. So yeah, this is working fine, and let me this run STM32. So this is okay. So successfully, let me check. Oh, this is the previous one. That's sorry, clear screen. Yeah, so we are not getting. Yeah, so I have already checked this because that user one we are not getting the data. If you are using user two, so then we get the data actually on the serial port. So, but I don't know why this is disabled just now in this video. Let me create one new. So let me check it is coming again or not. New file, STM file. So this is board selector and that G4. Yeah, next. And this is now UART test 5. Yeah. Next is mm, again it is disabled.
Does 3 work, sir?
No, 3 is also not works actually. So let me just check 3 of for the previous example. So that technically held this one and this was this. Yeah, so let me change this. So if I make this disable and make third enable. So now the PV that 10 and 11 pins are now enabled, and if I generate the code for that, it will change. So save all. So generate. So it will update the code actually, the previous code, and now you can see uh, here this is become now HUART3. So we need to change only this in our command, that main function. So while our that line is removed, Okay, that this one also. This first. So first we declare this, and after that we will write the same thing. Yeah. Okay. So HAL underscore UART underscore trans. So let's transmit this complete. Now 3, and we have the str and the size of str of str and time out. So this is 100. I'm giving this is the call, and now the delay. So HAL underscore UART. Sorry, no delay. So delay 1000. Okay, so now this code is done. If I check this, otherwise I have the another code which we have already done previous. That I'll check that. So let's build this. Okay, and that, run this. Okay, we are not getting anything. Okay, but I've done previously on the user 2 actually this one. Okay, so if you see the code for that, so that is this source in the main file. If you can see the this file, so this is also same HUR2 we have created, and then that this message we have written here, and inside the function we have just passed this. Okay, so this call, and this is the line. Okay, so remaining all these things we have set through the same configuration. So let's run this. It will work now. It was working previously, and now you can see we are getting this welcome for IIT. So user 2 is working fine. Okay, but it is disabled right now on the pin configuration. You can check your own that okay, it is
Sir,
enabled or not. Yes.
now will that would have got enabled, sir, in that pin configuration?
No, in yeah, in this that
No, if you
previous I
can
have
see
done,
the
yeah. So let
pin.
me open, yeah. So where is the I this one? Oh, I think some setting changed after the downloading, so it is asking for this also setup. Migrate, what is this option? There are two options to cross it. Migrate or delete it. Yeah, so this is the version effect actually. Not sure. So it is also asking to change. Okay, let's open continue. You can see here it is enabled. All are enabled actually. No error is coming.
Yes,
This
sir.
is due to some update or maybe something. I'll check this later. Okay, so you can do the coding from this HAL side also. So this is actually saves time, but by using this, you will not get the knowledge of the lower levels. So you can create these drivers by your own. So let me just tell you. So 1 second. So what is the actually uh, one? So Week-8 is also professor discussed about this the project structure things. So there are actually layers. So first is actually application layer. So that where actually we work. Okay, so okay. So after that, second layer is actually drivers layer. So that drivers, and next level is actually actual hardware. So where all this GPIO comes, GPIO and timers, and then UART, and other part is also comes, that is the lower level. So this driver layer actually is just a information that provide the information of the basics, like memory mapping of these GPIOs, and we have also the memory actually. Okay, so this inside this driver layer also we have the separate driver for each part. Okay, so not only this is not a single file, this is also a multiple file of the header file and source file. Okay, so header file means .h. Okay, that contains just a like this macros and basic information, and source file actually that contain the functionality. Okay, so for each part, suppose we are one driver file we can create for GPIOs only. Okay, one driver file we can create for timers, one driver file we can create for other UART. So all, and one, there is one file that is actually that is for system actually, that embedded that microcontroller, sorry, microcontroller basic. So which microcontroller actually we are using, so that driver file actually contains the data, so that h header file. So that means what is the memory mapping for that particular microcontroller. So where is the flash memory is actually start, what is the base address for flash memory, what is the base address for RAM, and we have another, there are multiple type of RAM like RAM, SRAM1, SRAM2. So what are the base address for those, and what are the base address for GPIOs, what are the base address for that, actually this is the main file related to the microcontroller that contains the base information for every part of the microcontroller. Okay, so like all base address. After that you can also create the another drivers, particularly for a part of like GPI. You can create one another header file and C file. Okay, so generally we create these two types of file, header file and C file. So this header file is just a definition of all the function, what type of functionality we are defining inside the source file, uh, that we create the macros for that only. So we can directly call the name of macro, and we can use the functionality of the, we can directly call the functionality from the source file. So these driver files actually are a predefined things. Like this, we are setting our bits to for GPIOs, mode register, that alternate function registers. All actually are defined by some names in these driver files, and no need to remember the address, and no need to remember the that particular bit. All these things, all these links are actually given by some labels. Actually, that label can easily be recall actually. Okay, so you can give the name to every that part which actually you need to set. Okay, during the creation of application. So okay, so you can give the name for easy name for your self during the creation of this driver. Okay, layer. And after that, at the time of application creation, you can simply call the functions or APIs. We generally give the name of these APIs, and directly call these APIs and pass the value, and perform your functionality. So like this HAL things we have done now, we have checked previously. We have set only some value, and we call the function for the transmit data, and that internally that is performing some function on the machine, that hardware level. But it is now abstracted from user. Okay, it is hidden from the user. So that complexity is hidden to the user actually. You can simply call the name and just pass the value and do the functionality. So
So,
yes,
under what circumstances will the driver layer has to be updated, sir?
uh, this if this driver layer is coming from the manufacturer, they actually time to time update it. And when you are updating your QIDE or all these things, so that package is actually updated time to time. But if you are creating your driver layer, okay, so that you are creating all driver files by your own, so that actually it will be fixed for any particular that controller.
Project.
If you no, that actually related to the hardware. So hardware
Okay.
will not be changed.
Oh, I see, I
Okay,
see. As long
so
as that hardware configuration is there, we don't need to
yeah,
update the driver unless
yeah,
there's a
no need
bug
to
or
update.
something.
Yeah, So that all memory locations all will remain same. That will not be updated. Okay, so if you are changing the hardware, so if you are changing another microcontroller, then you need to create the another driver file for that.
Let's say that some application and whatever all this is deployed in a large farm, okay, spread over a few kilometers. So is there any situation where drivers will have to be updated on maybe about 1,000 devices, something like that?
Uh,
Does a situation arise?
okay, so these things. So driver, this depends on the manufacturer thing. So same things, we cannot use our own driver to a large things. Okay, so where the multiple types of projects are running and multiple type of controller are there, we cannot use that as a common driver. So we will simply use the drivers that is actually related to the particular controller. Okay, so application. So because of that, this actually manufacturer created some common drivers, so that actually works for all controller. And you at the time of project creation, you actually include that driver corresponding to the microcontroller. So what type of microcontroller you are using, that package will be installed and that you can work. So same things, STM is creating some drivers, so that drivers will be very similar to most of the microcontrollers. If any functionality is changed in any microcontroller, so that part will only be changed. Other or remaining part will remain the same with the same naming also. If you are using this HAL for this board, so that function name will remain same for the another board also. So that same functionalities will remain the same names,
Okay.
API names.
The reason I'd asked is, some of these devices, they do what is called as a over-the-air updates. So at that time, they update the application or something a lower layer also. Some of these IoT devices, they keep talking about this over-the-air
Yeah,
updates and all that.
update. So
Is it at the
Uh,
application level?
Sir, I think these kind of things is a preprocessor things. So only use when we generate code, output code. So
no,
I think am I right?
he's asking about the that update is happening on the board or some code. Which level actually this update is happening?
Okay.
Okay, so this actually package is updating like this. So they are updating their IDE actually, and corresponding to the IDE, so they are changing something if some features are updated in the IDE.
For
But
example, electric vehicle, if you look at it as a set of embedded systems, they do over their updates and several things get changed.
so they actually change the program actually.
Application level.
Application level, they update the program. So here also this controller contains some programming. Okay, so
Okay.
they update the programming. So maybe some additional features are enabled after the update. So they actually keep this thing in the controller. So some maybe later time they can do some update. Okay, so they change the
Okay.
program and maybe some bug are there, some functionality is not working properly. So they update the code and just upload that code into the microcontroller. Okay, so that type of update comes. Otherwise, hardware cannot be changed. Only that application program can be changed in the that microcontroller.
Okay,
Other
because
things
sometimes
can't be changed. Yeah.
we have heard, when we're using, some devices at home, we keep hearing about firmware updates and all
Yeah,
that.
firmware update similar to your if we upload the different code in our microcontroller.
Okay, fine, sir.
Okay, so that code is actually changing.
Okay, sir. Thank you, sir.
In case of microprocessor, this driver detail where we can get? I mean, if you want to use the API for that.
So regarding this, you are talking about this HAL.
No, I'm talking about suppose we have Windows machine and sometime Apple. So in that there is a microprocessor, correct? And you want to write and access some hardware level layer. Then generally the driver is the one source. So where to get the detail of the driver in that
This is
case?
in the documentation.
Oh,
You
I mean
will
they are
you you will get all the details about the hardware, the documentation of that product.
No, because generally I was going through the Intel microprocessor. They don't provide any detail about hardware level. All the pin details,
So yeah, so
everything is hidden.
No, Intel microprocessor you are using, you are not using in the microcontroller, no? You are using in the system.
Correct.
So that actually they will not provide, because here all the functionalities is controlled by the operating system. Okay,
Okay.
you can't do anything related to that. All things are properly handled by the operating system, which is provided by the manufacturer. Okay, so you
Okay.
can't reach at that level. You can't change anything at that level. Okay, but
Okay.
this microcontroller is just a that device where we can control all the things, operations, and that settings, all these things. So this is just a board which is provided for the small type of functionality, small type of operation, which we can say. Otherwise,
Okay.
regarding you, if you're talking about the computer system, so that you have to become a manufacturer for like a operating system. Those who are working on the development of the operating system, they are actually managing the that lower level. They are just
Okay.
working on the lower level system.
I understood. Yeah.
Okay. Okay, so next session, I'll just explain this driver development also in the detail. Okay, so how we can create a proper project structure, and regarding this header files and this source file as a driver. So that is also one important things. Okay, so you should know how the driver actually developed. Okay.
Yeah.
Yeah, other things you can just do all more experiments to understand better this. Okay.
Yeah. I mean, a very good session. Thank you.
Okay,
Thank you,
thank
sir.
you.
Excellent session.
Yeah,
Yeah. Very
thanks.
good session. Yeah. Thank you.
Okay, thanks. Bye, everyone.
Good night, sir.
Good night.
Good night.